all electromagnetic waves travel in a vacuum at the speed of light. And the speed of light is 3.0 times 10 to the 8th meters per second. All right, we'll just consider that a constant, so no sig figs for that, or unlimited sig figs, all right? The symbol for the speed of light is a lowercase c, so it's c equals 3.0 times 10 to the 8th meters per second. Each complete wave cycle begins at the origin and then returns to the origin. So now we're going to talk about wave structure, all right? So a wave starts at the origin and then it'll return to the origin. So that's what our origin is here. So if our wave starts by going down, it'll eventually come on back to that origin. Now, a complete wave cycle has a lower part and an upper part, all right? The upper part, the top of it's called the crest. The lower part, it's a trough. And if you're a surfer or know anything about oceanography, they use the same terms for waves out in the ocean, all right? The amplitude is the distance from the origin to the crest, which is the same as the origin to the trough, all right? So amplitude is the same either way, all right? And then this wave is traveling at the speed of light, all right? That number, 3.0 times 10 to the 8th meters per second. The wavelength is from one crest to another crest, or from any corresponding point to the same one. So this, you have to do the bottom, you have to do the top, but then this would also be the wavelength down here. And they would be the same, all right? The measurement would be the same. Now it's wavelength, so it's in meters or nanometers, right? Depending on whatever units they give you, all right? So amplitude is from the origin to the crest. The wavelength is in lambda is the symbol for it, all right? And it kind of looks like an upside down Y. And that's the distance between two crests, and it's the same as the distance between two of any other spots on there. It would be the same distance, all right? Because if you change the wavelength, you would change the light. If you change it and it's visible light, you would change the color. Or if it's something like gamma, you could change it into X-ray, like it would be different, all right? Okay, any questions labeling any of that part, the wave? No? Okay. All right, so now frequency, this is another Greek letter. Here we have the nu. Kind of looks like a cross between a U and a V. You can write it like this, you can write it like as a V, that's fine. It's the number of wave cycles to pass a given point per unit of time. And it sounds complicated, but it's not. And I'll show you what an example looks like. Frequency and wavelength are inversely related. So as one goes up, the other goes down. So I'm going to draw a couple different waves here. So this is 0 seconds, and then this would be 1 second. So when you do like physics experiments and stuff, you usually have a timer. So whenever you click the timer, then it starts counting. So we click the timer at 0, and then we stop it at 1 second, all right? And we're gonna see what our waves look like, all right? So we'll have 3 waves. One will look like this, maybe another one looks like this, and then our third one looks like this. And so they all traveled the same distance, right? Because they moved at the speed of light. All right, but how they traveled looks different for all of them, right? And it's all in 1 second. Okay, wavelengths. Let's look at the wavelength of the top one. So from here to here, that's its wavelength. This one, the wavelength is from here to here. And then this one wavelength is from here to here, all right? So what, if you were to compare the top one and the bottom one, how would you compare their wavelengths? The top one's, you could say longer, right? Bottom one's shorter. So the top one's gonna be longer, the bottom one's gonna be shorter, right? Okay, let's talk frequency. Now, frequency, we use this word in English a lot, and it means pretty much the same thing, because if I asked you which one has a higher frequency, you'd be able to tell me without really understanding the the definition of it real well. Out of the top one and the bottom one, which one has a higher frequency? The bottom one, right? Because it has more bumps, right? It goes through the process of a wave more times. It goes up and down, more down here. So yeah, this has a frequency. How many times does this do this in 1 second? That's the technical definition of a frequency, all right? Because it says per unit time, all right? So for this frequency, and that was our V-looking symbol, all right? This frequency would be lower, and this frequency would be higher. There'd be a higher frequency for the bottom. Everybody cool with that? Make sense? Yeah? Okay. Now the last thing that we didn't really talk about on this page, but we have kind of talked about, is energy. Which has the higher energy out of the three, the highest energy? The bottom one, right? Bottom one, it looks like it's doing more stuff, right? If you think about the video where they talked about on the ship, where it's kind of rocking slowly back and forth, it seems like low energy. That's kind of the top. And this one, it's going, oscillating a lot. It's going up and down a lot. So this would have higher energy. This would have lower energy. All right. Now notice wavelength, which is the upside down Y looking thing, wavelength, the lambda, they're inversely related to the other two. So if your wavelength is higher or longer, your frequency is going to be shorter. Your energy is lower. All right. With this, it's the opposite. Your wavelength is going to be real short. Your frequency and energy are going to be greater. All right. Any questions with that? Now we can even look at this with the chart we have. So let's go back. Oh, you had it right here. Where the wavelength here is real short, right? Wavelength is short here. What did we say about the energy on this side? Yeah, it's going to be a higher energy, right? Because the wavelength is lower. So what do we expect the frequency to be on this side? Yeah, frequency on this side is going to be higher. If we were to draw gamma, I mean, it would be a whole bunch of up and downs really close together, right? Because the wavelengths are so short. This over here, radio waves, would be much longer, and that's not even close to how long it would actually be. This is 10,000 meters. That's a really long distance. Here, this is 1 meter. So this would be, you know, from about here to here. That would be its wavelength. And this would be times 10 to the negative 12 meters, like such a tiny amount, all right? So energy over here is lower, but the wavelength is going to be bigger, and also the frequency will be lower as well, because it'll happen less times. Does that make sense?